Hello, my curious friend, and a very warm welcome to the Deepfield channel. Tonight, we are going to journey into one of the most mind-bending territories that science has ever dared to chart. The question of why there is something it is like to be you, why an inner experience is unfolding right now as you listen to these words, and whether this experience has roots so deep that they reach into the very heart of reality's fabric. We will ask, with all the tranquility the night allows, whether consciousness is a quantum mystery, and I promise to try not to make the subject so unsettlingly fascinating that it keeps you awake, though I admit the odds might not be entirely in my favour. But before we dive into this enigma, I would love to know in the comments which corner of the globe you're tuning in from tonight. And if you are feeling too relaxed to type, just leave a simple hello. It might seem like a small thing, but that tiny gesture signals to the platform that our space is welcoming, helping us bring more weary minds here to unwind with us. If you enjoy our scientific journeys, please drop a like and subscribe. And to those of you who are already part of our community, thank you so much. If you want to get even closer, consider becoming a channel member. Members receive early access to videos before anyone else. The link is waiting for you in the description. Now, wherever you happen to be, find a deeply comfortable position. If sleep begins to call to you, accept the invitation. Let us begin. There is a moment that happens every single night, yet almost no one pauses to contemplate it. It is the exact instant when you are still awake, and a second later, you simply are not. There is no darkness that you perceive, no silence that you hear, no passage of time that you register. There is a you who is thinking, and then there is nothing. And then there is a you waking up as if that void never occurred. This interval, this brief collapse of experience, is perhaps the strangest thing that happens to any human being on any ordinary day. And yet we live our entire lives without ever looking at it closely. Consciousness is exactly like this. It is the closest thing to you in existence, closer than your own skin, more intimate than any memory, more constant than any isolated thought. It is the stage upon which everything happens, and at the same time, it remains completely invisible to any instrument science has ever built. No scalpel has ever found it. No microscope has ever photographed it. No brain scanner has revealed exactly where it resides, or if it even resides in one specific place. Consciousness is the only phenomenon in the universe we know with absolute certainty from the inside, yet it remains utterly mysterious when we attempt to study it from the outside. Think for a moment about what it means to perceive the colour red, not the physical process, which we understand reasonably well. Light of a specific wavelength enters the eye, stimulates specialized cells in the retina, produces electrical signals that travel down the optic nerve and arrive at the visual cortex. All of this is biochemistry, it is physics, it is measurable. But there is something beyond that. There is the sensation of redness. There is what it is like to be you looking at that color. There is an internal, subjective, irreducible quality that philosophers call qualia, and it does not appear in any equation, in any measurement, in any objective description of the process. You can describe the wavelength, the neural activation, the signal pathway, but the sensation itself slips through all these descriptions like water through your fingers. This abyss between the physical description of a brain process and the subjective experience that accompanies it has a name. The philosopher David Chalmers dubbed it the hard problem of consciousness, in contrast to the so-called easy problems, which encompass all the questions about how the brain processes information, integrates data, controls behavior, and produces reports about its own states. The easy problems are called so not because they are simple, but because they are, at least in principle, solvable, using the standard tools of science. The hard problem is not, because it asks something that no amount of functional description can answer. Why is this processing accompanied by experience? Why doesn't all of this happen in the dark without anyone home to experience it? There is a widespread myth worth dispelling right from the start. The idea that neuroscience has already solved, or is on the verge of solving, the issue of consciousness. It is true that neuroscience has learned extraordinary things about the brain in recent decades. We know that certain regions are associated with certain functions. We know that damage to specific areas results in specific losses of ability. We know that consciousness shifts when certain neurotransmitters are present or absent. All of this is real and valuable, but none of these discoveries have come anywhere close to explaining why there is subjective experience instead of just mechanical processing. Neuroscience has mapped the neural correlates of consciousness, that is, the brain patterns that accompany conscious states. But correlation is not explanation. The fact that certain activity in the prefrontal cortex coincides with a state of conscious attention does not tell us why that activity is accompanied by something that feels like anything at all. The human brain is, by any metric you choose to use, the most complex structure we know of in the observable universe. It contains roughly 100 billion neurons, a number so vast it is genuinely difficult to comprehend. If you counted 1 neuron per second, it would take you over 3,000 years to reach the end. Each of these neurons can form connections with thousands of others, and the total number of synapses in the adult brain is estimated to be around 100 trillion, which means there are more connections inside your skull than there are estimated stars in the Milky Way. This organ, weighing about 3 pounds and possessing the consistency of soft tofu, running on the energy equivalent of a dim light bulb, somehow produces love, longing, the contemplation of abstract ideas, and the sensation that there is a self experiencing it all. The individual neuron is a cell, a living cell with a nucleus, a membrane, mitochondria, and all the standard biochemical machinery common to biology. But what makes neurons special is their ability to generate and transmit electrical signals. The neuron's membrane maintains an electrical potential difference between its interior and exterior, sustained by the controlled movement of sodium, potassium, calcium, and chloride ions through specialized protein channels. When sufficient stimuli arrive, this potential difference rapidly collapses in a wave that travels the length of the neuron, the so-called action potential, and upon reaching the axon terminal, it triggers the release of chemical messengers, neurotransmitters, which cross the synaptic cleft and bind to receptors on the next neuron. This is the basic alphabet with which the brain writes every thought, every emotion, every perception. But there is something that begins to catch the attention of physicists and philosophers when they examine this process through a finer lens. The action potential, although frequently described as an electrical phenomenon, involves at its core events that occur on the scale of individual molecules, single proteins and ion channels that open and close in response to voltage changes. And at this scale, the classical world of Newtonian physics begins to give way to another regime of laws, a realm where particles lack defined positions until they are observed, where two objects can be correlated in ways that defy any notion of locality, and where chance is not merely ignorance about hidden causes, but an irreducible feature of reality. This regime is quantum mechanics. Quantum mechanics is the most precise and thoroughly confirmed physical theory humanity has ever produced. Its predictions have been tested in experiments of extraordinary precision and have never failed. And yet, it describes a universe that no human being can truly visualize, because it intuitively violates almost everything our daily experience has taught us about how things work. A quantum particle, like an electron, is nowhere in particular before it is measured. It exists in a superposition of multiple possibilities simultaneously, described by a mathematical entity called the wave function, which encodes the probabilities of every possible outcome of a measurement. When the measurement occurs, we say the wave function collapses, and the electron finally appears in a definite location. But what exactly constitutes a measurement, and what triggers this collapse? remain open and deeply debated questions in theoretical physics. There is another quantum phenomenon that is even more bewildering, known as entanglement. When two particles interact in a specific manner, they can become entangled, meaning the quantum state of one cannot be described independently of the state of the other, no matter how far apart they are subsequently separated. If you measure a property of one entangled particle and obtain a certain result, the partner particle instantly assumes the correlated state, even if it is on the other side of the universe. Einstein called this spooky action at a distance and was profoundly uncomfortable with the idea. However, experiments conducted since the 1970s, and continuously refined ever since, have demonstrated that entanglement is real, that it cannot be explained by any theory assuming particles possess definite properties prior to measurement, and that the correlation between entangled particles systematically violates the limits established by what we call Bell's inequalities. What does all of this have to do with consciousness? That is the question that will accompany us throughout the night, and it has an intriguing history, one that begins long before any formal theory and traverses 20th century physics in ways that still generate equal parts controversy and fascination today. Because right from the early days of quantum mechanics, when the founders were trying to understand what the theory actually meant regarding the nature of reality, the concept of the observer stepped onto center stage in ways that deeply disturbed those who believed physics should be an objective description of a world existing independently of any mind. Some of the greatest physicists of the past century suggested that perhaps the mind is not merely a passive observer of the quantum world, but that there might be a deeper, more fundamental link between the nature of subjective experience and the most intimate structure of physical reality. The brain that experiences, the electron that superposes, the observer that collapses, the mind that asks why there is something it is like to be it. These are the threads we will attempt to weave together carefully, without rushing, in the gentle cadence of this night. There is something dizzying about this investigation, but also something profoundly peaceful, because asking these questions does not require you to arrive at an answer. It only requires you to inhabit the question with attention and openness. And as you wonder where the energy comes from that animates this entire prodigious system, which sustains the relentless glow of 100 billion neurons conversing with one another, which fuels the stage where experience occurs, let that question float lightly, without urgency, like a leaf upon the calm surface of a nocturnal lake. Consider for a moment what occurs when you strike a match to light a candle in a pitch-black room. Before anything else, before the illumination reaches the walls or the warmth begins to radiate into the air, there is that fleeting instant where the flame is still being born, where the chemical energy stored in the wax begins its long transformation into light, into heat, into the motion of molecules, into photons traveling in straight lines until they strike the white paint of the wall. This entire process, from solid wax to the light that brightens the space, obeys a logic that the universe established long before any eye existed to gaze upon a flame. And the human brain, that 3-pound organ housed within the skull that somehow generates the entire richness of conscious experience, also obeys this exact same logic. It requires energy, a considerable and steady supply of it, delivered without interruption, allowing for no tolerable pauses. The brain consumes a disproportionate fraction of all the energy the body produces. In terms of body weight, it represents roughly 2% of an adult human's total mass. Yet this small volume of nervous tissue consumes approximately 20% of all the oxygen the body processes, and a similar portion of the glucose circulating in the blood. This is remarkable not just as biological fact, but as an indicator of an extraordinary functional demand. The brain never rests. Even during sleep, neurons continue firing, synapses continue transmitting signals, and the processes of memory consolidation and metabolic cleanup continue occurring with vigor. The The difference between the awake brain and the sleeping brain is not the difference between an engine turned on and an engine turned off. It is more akin to the difference between an orchestra performing a symphony and the same orchestra running a low-intensity rehearsal, where different sections take turns being active, but the ensemble never entirely ceases. Glucose is the preferred fuel for this system. It reaches the brain tissue through an extraordinarily dense vascular network, with capillaries so fine and numerous that almost no nerve cell is more than a few micrometers away from a blood vessel. When a neuron fires, when it generates that electrical impulse called an action potential, it needs to recalibrate its cell membrane, restoring the ion gradients that were disrupted by the firing, and this costs energy. The sodium-potassium pump, a protein embedded in the neuron's membrane that functions literally as a tiny molecular machine, uses adenosine triphosphate molecules to expel sodium ions and absorb potassium ions, maintaining that electrical imbalance which is the necessary condition for the next firing to be possible. Without energy, this pump stops. Without the pump working, the neuron loses its polarity. Without polarity, no new signal can be generated. Within minutes, without oxygen, neurons begin to die. Consciousness, therefore, is not an ethereal thing hovering above biology. It is viscerally anchored in a continuous and demanding metabolic process. But this raises a question that goes beyond simple physiology. Energy courses through the brain constantly. Electrical signals leap from neuron to neuron across synapses. Neurotransmitters are released, diffuse across the synaptic cleft, bind to receptors, and activate biochemical cascades. All of this is physical process. All of this is matter interacting with matter according to the laws of physics and chemistry. And yet, at some point in this chain of events, something emerges that is not satisfactorily described by any biochemistry textbook. The sensation of being, the taste of coffee, the pain of a loss, the beauty of a melody. Where does this leap come from? What physical law describes the transformation of an ionic current into a feeling? Classical physics, the framework Newton systematized and which for centuries formed the foundation of all natural science, treats the universe as a grand deterministic machine. Particles with well-defined positions and velocities, forces acting upon them in predictable ways, trajectories that can in principle be calculated with arbitrary precision, provided the initial conditions are known. In this universe, consciousness would be an epiphenomenon, a byproduct with no causal power, like the shadow a water wheel casts on a wall. The shadow exists, but it is not what makes the wheel turn. The mind would merely be the passive reflection of purely mechanical brain processes. This view possesses an austere elegance, but it leaves completely unexplained why there is a subjective shadow to begin with. Why does the wheel produce a shadow that feels? It was in the early 20th century that this view began to crack in profound and unexpected ways. The first sign was the so-called black body problem, when physicists tried to calculate how much heat and light a perfectly absorbing object should emit when heated. The equations of classical physics produced an absurd result. The object should emit an infinite amount of energy at high frequencies. This became known as the ultraviolet catastrophe, and its name says everything about the embarrassment it caused. In 1900, a German physicist named Max Planck proposed a solution that he himself considered provisional and mathematically artificial. What if energy could not flow continuously but only in small discrete packets, in fixed amounts he called quanta? Planck did not know exactly what he was doing. He was, in words he would later use, performing an act of despair, trying to save physics from an embarrassing contradiction using a mathematical trick. But the trick worked, and in working, it opened a door that physics would never be able to close. Energy is not continuous. It comes in portions. This simple and unsettling discovery is the foundation of all quantum physics, and it radically changes how one can think about what is real, what energy is, and what the process of observation entails. Albert Einstein, who was then a young clerk in a patent office in Bern, read Planck's work and took it further. In 1905, he used the idea of quanta to explain the photoelectric effect, the phenomenon where certain metals eject electrons when illuminated. Classical physics predicted that increasing the intensity of the light should eventually liberate electrons, regardless of frequency. Einstein showed that what determined whether electrons would be released was not the intensity, but the frequency of the light. Light, therefore, was not just a continuous wave as Maxwell had demonstrated in the previous century. It also behaved as a particle, travelling in packets of energy called photons. This wave-particle duality would become the backbone of all the strangeness that followed. Niels Bohr, a Danish physicist with a contemplative personality and deliberately imprecise language, developed over the following years a model of the atom in which electrons could only occupy certain discrete orbits, specific allowed energy levels, and that when jumping between these levels, they emitted or absorbed exactly one quantum of energy, a photon of precise frequency. The atom was not a miniature solar system with planets in continuous orbits. It was something much stranger, with electrons existing in discrete states that only revealed their position when interacting with the environment in some measurable way. Bohr would remain obsessed for the rest of his life with the philosophical implications of this, with the question of whether electrons had defined properties before being measured, or if the measurement somehow created them. Heisenberg, who was a student of Bohr, formalized this strangeness in his uncertainty principle. You cannot simultaneously know both the position and momentum of a particle with arbitrary precision, not because your instruments are inaccurate, but because nature at its most fundamental level does not contain this information simultaneously. Uncertainty is not our ignorance about a world that exists with full determination. Uncertainty is a property of reality itself. When Heisenberg presented this result, Einstein was deeply disturbed. He spent years trying to find flaws in the argument, proposing increasingly elaborate thought experiments to show that uncertainty was merely apparent, but the principle withstood every attempt. The universe at the quantum scale does not play chess with pieces in defined positions. It plays a much hazier game, whose rules only reveal themselves at the moment of the move. The fundamental imbalance that makes all this physics work is precisely this: the difference between the undefined state of a particle before measurement and the defined state after it. Before measurement, an electron can be described mathematically by a wave function, a mathematical object that distributes probabilities across many possible positions simultaneously. The electron is not in just one place. It is in a superposition of places, in a sort of fog of possibilities that mathematics describes perfectly, but which the human imagination resists visualizing. After measurement, the wave function collapses. One possibility becomes reality, the others vanish. The electron now has a position. This collapse is the deepest fissure in modern physics. No one knows exactly what causes it. The Schrödinger equation, which describes how the wave function evolves over time, is one of the most precise equations science has ever produced. It has never been observed violating any experimental prediction, but it does not describe the collapse. The collapse happens outside the equation, when something we call measurement occurs, when the quantum system interacts in some way with a larger system, with a detector, with an instrument, with the environment. And here, at this precise point, the question of consciousness enters through the most unlikely door. What counts as an observation? What exactly constitutes a measurement? Erwin Schrödinger, who had created the wave equation during a retreat in the Alps in December 1925, was so disturbed by the implications of his own creation that he spent years trying to show the probabilistic interpretation was wrong. He formulated his famous thought experiment with the cat to demonstrate the absurdity. A cat locked in a box with a quantum mechanism that may or may not release poison is, according to the equation, simultaneously alive and dead until the box is opened. Schrödinger wanted to show the interpretation must be wrong, because no one truly believes cats exist in superpositions. But quantum physics survived the cat. Superposition is real. The absurdity is not an error of the theory. It is a property of the world. And it is here that the question about consciousness fits into this scenario with a particular unsettling nature. If the collapse of the wave function requires an observation, and if the chain of instruments and detectors can themselves be described by wave functions that entangle with one another in a process called entanglement, where does this chain end? When a photon travels through space and finally meets the retina of a human eye, and the nerve signal travels down the optic nerve, and the visual cortex processes the information, and at some point the person becomes conscious of having seen the light. Was it consciousness that collapsed the wave function? This question, which sounds extravagant, was taken completely seriously by some of the greatest physicists of the 20th century, including John von Neumann himself, who tried to find the precise point in the nervous chain where the collapse should be attributed. A neuron fires. This is a physical event, governed by the laws of electrochemistry. But this firing propagates, converges with other firings, and creates patterns of activity that spread across vast networks of the cortex. Every synapse that is activated, every action potential that propagates, every ripple of activity that traverses the nervous tissue is a local mechanism operating according to well-established rules. And now, before going further, before trying to describe what happens when this mechanism repeats not once, but millions of times per second, in 100 billion neurons forming around 100 trillion connections with one another, before trying to map what emerges from this dizzying scale, it is worth sitting with the question that this scale evokes all by itself. What happens when this tiny local mechanism, this single firing of a single neuron, repeats in this unimaginable proportion, in this network of complexity that has no known parallel in the observable universe? When the activity of a single neuron propagates to its immediate neighbors, something begins to happen that transcends the simple addition of identical events. It is not a matter of adding firings like adding stones to a pile. The propagation creates temporal relationships between the firings, and these temporal relationships are the raw material of something entirely new. A neuron that fires a fraction of a millisecond before another is not just contributing one more unit of activity. It is modifying the context in which the second neuron will fire, altering the probability that a third and a fourth will join, and thus creating a sequence that carries within it a sort of history, a short-term memory embedded in the very dynamics of the propagation. This phenomenon was formally described in neuroscience as synchronization, but the technical word hides something profoundly strange. Synchronization between neurons does not mean they start firing at exactly the same time, like metronomes set to a single rhythm. It means something more subtle and more powerful, that the firings begin to have consistent phase relationships with one another, which repeat and sustain themselves over time. Two synchronized neurons might fire in alternation, one right after the other, always with the same interval, like two rowers who have found the common rhythm that makes them advance effortlessly. This temporal consistency is the first step toward large-scale organization. The neuroscientist Wolf Singer was one of the first to systematically document that distinct regions of the visual cortex in cats exhibit this precise synchronization when the animal perceives a cohesive object. This occurred in a series of experiments throughout the final decades of the 20th century. What Singer and his colleagues observed was that neurons separated by considerable distances within the cortex began to oscillate in unison when responding to what appeared to be a single object, and stopped oscillating together when the visual elements were perceived as separate objects. The brain seemed to be using time, the temporal coincidence of firings, as a language to declare what belonged to what. This discovery raised a hypothesis that became known as the binding by synchronization hypothesis, and it brought with it a radically different perspective on how the brain organizes its own activity. If different cortical regions can synchronize temporally to represent a single unified object, then the coherence of perceptual experience might not be contained in any specific place in the brain, but distributed in the temporal fabric of the relationships between firings. The unity of a perceived object would not be a property of a special neuron somewhere central, but a relational property emerging from the synchronization of many neuronal populations simultaneously. What emerges from these large-scale synchronizations are brain oscillations, the rhythms that electroencephalography records as waves moving across the surface of the skull. These waves have characteristic frequencies that neuroscientists have learned to name. The delta waves, slow and deep, predominant in dreamless sleep. The theta waves, associated with memory and spatial navigation. The alpha waves, that tranquil rhythm that appears when the eyes close and the mind relaxes. The beta waves, faster, linked to active thought and directed attention. And the gamma waves, the fastest of all, oscillating dozens of times per second, and which appear with remarkable consistency during moments of integrated processing and conscious perception. The discovery of gamma waves as a correlate of conscious states was one of the most stimulating moments in contemporary neuroscience. Francis Crick, the very same Francis Crick who decades earlier had helped unravel the structure of DNA, dedicated the final phase of his scientific career to the question of consciousness. In collaboration with Christoph Koch, Crick proposed that gamma oscillations, particularly those occurring around 40 cycles per second, could be the mechanism by which the brain binds different representations into a unified experience. The proposal was elegant. If the problem of consciousness was understanding how information processed in distinct modules became a single, integrated experience, perhaps the answer lay in the rhythmic synchronization of these regions into a single collective pulse. The idea did not survive without contestation. Subsequent experiments showed that gamma oscillations are not simply the marker of consciousness that Crick and Koch hoped they would be. Sometimes they are present without apparent consciousness, sometimes absent in clearly conscious states. But the contestation of the specific hypothesis opens space for something richer. The understanding that the conscious brain does not have a single temporal marker, but a dynamic landscape of rhythms that interact, couple, decouple, and continuously reorganize. Consciousness, if it has an oscillatory correlate, is perhaps more like an orchestra than a metronome. This image of the orchestra deserves to be inhabited with care. In a real orchestra, there is a conductor, a score, musicians who have rehearsed. In the brain, none of this exists. There is no central region issuing commands to synchronize all the others. There is no pre-written score dictating which frequency should dominate at which moment. What exists is something more surprising. Order emerges from the local coupling between regions responding to one another, and from this local coupling, a global coherence is born that no single region could have produced alone. It is an orchestra without a conductor, where the music arises because each musician hears the others and adjusts their rhythm to what they hear, and from all these simultaneous adjustments emerges something that has structure, coherence, and that can change from one instant to the next. Mathematicians have a name for systems that behave this way: complex adaptive systems. And the brain is perhaps the most elaborate example of a complex adaptive system that nature has produced. Its topology, the way its connections are distributed, is neither random nor completely regular. It is what scientists call a small world network, a structure in which there are many dense local connections and some long-range connections linking distant regions to one another. This architecture is not trivial. It was mathematically described by Duncan Watts and Stephen Strogatz in the late 1990s while studying networks in general, and when neuroscientists applied their tools to the brain, they found this small world network signature with remarkable consistency. What a small world network does specially is allow local perturbations to propagate rapidly to distant regions, without the entire network needing to be directly connected to everything else. It is like the phenomenon of 6 degrees of separation between people. 2 individuals on opposite continents can be connected by a surprisingly short chain of mutual acquaintances, even though most people primarily know those around them. In the brain, this means that a local activation in some region of the visual cortex can, in extraordinarily short time, influence regions of the frontal lobe involved with planning and decision-making. The speed of global integration this allows is part of what makes consciousness possible as a unified phenomenon. Giulio Tononi, an Italian neuroscientist working in the United States, developed over decades a theory that attempts to formally capture this integrative quality. His integrated information theory proposes that consciousness is identical to a specific quantity, the amount of information a system generates beyond the sum of the information generated by its parts. Tononi called this quantity phi, and argued that systems with high phi are conscious, while systems with zero phi, like a collection of independent neurons that never interact, have no subjective experience whatsoever. The formal beauty of Tononi's theory lies in the fact that it attempts to answer not only when a system is conscious, but why consciousness exists in integrated systems and not in others. A computer processor can perform extraordinarily complex calculations, but if its architecture is such that different modules do not influence each other beyond what is necessary to perform the task, its phi will be low, and the theory predicts there will be no subjective experience inside. The brain, by contrast, has an architecture that seems specifically optimized to maximize the integration of information from diverse sources, long-range connections, oscillatory rhythms that couple distant regions, the small world network topology. All of this could be interpreted as adaptations that elevate the system's phi. There is a specific structure that concentrates many of these long-range connections, the thalamus. Situated almost at the geometric center of the brain, the thalamus is often described as a sensory relay, a way station for information coming from the sense organs on its way to the cortex. But this description is deceptively simple. The thalamus maintains incredibly dense bidirectional connections with virtually all regions of the cortex, and there is growing evidence that it actively participates in coordinating cortical rhythms, functioning somewhat like a pacemaker that synchronizes regions that would otherwise have difficulty coupling directly. When the thalamus is damaged in certain ways, consciousness does not merely degrade, it completely collapses, even if extensive cortical regions remain intact and functional. Francis Crick, in the final years of his life, turned his attention to an even smaller and more mysterious structure called the claustrum, a thin sheet of neurons hidden beneath the insular cortex that maintains connections with almost all cortical regions. Crick believed the claustrum could be the coordinator of unified consciousness, the hidden conductor everyone says does not exist. The hypothesis remains controversial and difficult to test, but the fact that a structure of such peculiar geometry, thin as a leaf and extending across much of the brain's length, has such comprehensive connectivity, is in itself an indication that the geometry of connections matters just as much as their quantity, and it matters in ways we are still learning to describe. The cortical hierarchy, the organization of the cortex into layers, ranging from primary regions processing simple features to associative regions, integrating abstract representations, creates an organizational gradient through which information flows in multiple directions simultaneously. It is not an assembly line where one stage finishes before the next begins. It is a network with constant feedback, where high-level regions send signals back to low-level regions, modifying how they process subsequent information. This bidirectional flow, which neuroscientists call top-down and bottom-up processing operating simultaneously, is another characteristic that distinguishes the architecture of the conscious brain from any simple computational system. What all these patterns, the oscillations, the integration, the network topology, the hierarchical geometry, have in common is that none of them were planned. They emerged over hundreds of millions of years of evolution from selective pressures that never had consciousness as an explicit goal. Evolution does not know where it is going. It merely preserves what works best, what allows the organism to survive and reproduce. And what worked was, apparently, building a system that integrates information in increasingly sophisticated ways, that creates increasingly rich internal representations of the environment, that anticipates the future with ever greater precision. And at some point along this path, something appeared that no natural selection had explicitly demanded: experience. These emergent patterns that evolution built would function, in a sense, without any additional phenomenon. The oscillations could oscillate, the networks could synchronize, the information could integrate. All of this could happen mechanically through pure physics, without there necessarily being anything it felt like from the inside. And it is exactly here that the explanation via large-scale organization begins to show its seams. Because no matter how precise the description of the patterns, no matter how detailed the map of connections, no matter how elegant the mathematical formalization of face, something is left out. The patterns described so far would be equally possible, at least in principle, in a system that lacked an ingredient we have not yet named. An ingredient that some physicists have begun to suspect might amplify, or even make possible, the transition from pattern to experience. This missing ingredient has a name that seems too technical for the lightness of what it represents, but which physicists and philosophers who have studied the mind for decades cannot avoid pronouncing with a certain restrained reverence: quantum coherence. The word coherence, in the vocabulary of physics, does not simply mean harmony or organization. It describes something much more precise and, in a sense, much stranger. Two or more quantum systems are coherent with each other when their wave functions are intertwined in such a way that the state of one cannot be described independently of the state of the other, when they form, so to speak, a single entity distributed in space, a totality that does not admit being divided into parts without something essential being lost in the act of division. To understand why this matters so much here, it is worth pausing to contemplate what happens when two quantum systems are not coherent. Each particle or structure follows its own trajectory, obeys its own probability, carries its own uncertainty. When many of these structures come together, as in the human brain with its roughly 86 billion neurons, the collective behavior can be complex, but it is still, in principle, reducible to the parts. It is complicated, but it is not mysterious in a way that surpasses what classical mechanics could, with enough patience and computing power, describe. Now imagine that some of these structures enter quantum coherence. Imagine that separate parts of the system begin to share an indivisible quantum state. The system ceases to be a collection of parts and becomes, literally, a unit extending across multiple locations simultaneously. And it is precisely here that some physicists have begun to suspect something new could emerge. Roger Penrose was the first to articulate, in a mathematically rigorous way, the suspicion that consciousness could not be computational in the ordinary sense. His argument stemmed from a surprising result in mathematical logic, Gödel's theorem, which demonstrated that any formal system powerful enough to describe arithmetic contains true statements that cannot be proven within that system. Penrose argued that the human mind can perceive these truths in a way no fixed algorithm could accomplish. And if the mind is not an algorithm, it cannot be explained by any physics that is, in its essence, deterministic or computationally closed. This would mean quantum physics, with its element of genuine indeterminism, would need to be invoked. But not just any aspect of quantum physics. Penrose pointed to a very specific place: the collapse of the wave function. In standard quantum mechanics, a quantum system can exist in a superposition of multiple states simultaneously. an electron can have spin up and spin down at the same time until it is measured, at which point the system collapses to a definite state. What causes this collapse is one of the oldest and most uncomfortable questions in all of physics. Some interpretations say it is the act of measurement. Others say all states continue existing in parallel branches of the universe. And still others, like the one Penrose favours, say the collapse is an objective physical process that occurs when the superposition reaches a certain threshold of gravitational separation. Penrose called this process objective reduction, and he proposed that this process, occurring within the brain, could be the physical moment when conscious experience anchors itself. The name he gave to the complete theory, developed in collaboration with anesthesiologist Stuart Hameroff, is orchestrated objective reduction, or ORC-QA, which in English sounds like a musical chord which does not seem entirely accidental. Hameroff brought to the partnership an ingredient Penrose had not contemplated deeply: microtubulars, protein structures that exist inside every neuron. Microtubules are elements of the cellular cytoskeleton, the beams and columns that maintain the cell's shape and organize the transport of molecules through its interior. For decades, they were viewed as pure structure, a cellular scaffolding with no relevant computational function. Hameroff proposed they were much more than that. Microtubules are polymers formed by dimers of a protein called tubulin. Each dimer exists in two distinct conformational states, like a switch that can be on or off, and Hameroff argued that these conformational states could exist in quantum superposition, that the tubulin could be in both states simultaneously, until Penrose's objective reduction process collapsed the superposition. This collapse, according to the theory, would not be random nor deterministic in the classical sense. It would be orchestrated by biological connections, associated proteins, electrical signals, neural oscillations, which would coordinate the timing and pattern of the collapse. The result would be a sequence of quantum events that would follow no predefined algorithm, but which would not be purely random either. They would be, in a sense, decisions emerging from the boundary between determinism and indeterminacy. The theory was met with considerable skepticism when proposed, and much of that skepticism still persists. The most frequent argument from critics is that of decoherence. In warm, wet biological systems, quantum coherence tends to dissipate extremely quickly. Constant interactions with the environment, molecular collisions, thermal heat, all of this tends to destroy quantum coherence before it can have any macroscopic effect. At room temperature, the coherence time of simple molecular structures is on the order of femtoseconds, millionths of a second, time enough for a photon to traverse only a tiny fraction of a human hair. It would be impossible, critics argued, for any quantum coherence to survive long enough in microtubules to orchestrate something as slow and complex as conscious thought. But then something unexpected happened. And it happened not in neuroscience, but in biochemistry. Researchers studying photosynthesis, the process by which plants convert sunlight into chemical energy, discovered that the extraordinary efficiency of this process, close to 100% in transferring energy from the collecting antenna to the reaction center, depended on quantum effects. The energy did not travel a single path, like a ball rolling down a track, but traversed multiple paths simultaneously, like a wave branching through all possibilities at once, and arrived at the destination through constructive interference between these possibilities. It was quantum coherence inside a protein at normal biological temperatures in an aqueous environment, lasting for hundreds of femtoseconds. What had been considered impossible was happening inside a green leaf in the sun. Similar discoveries accumulated. Migratory birds seem to use a quantum mechanism called cryptochrome magnetoreception to detect the Earth's magnetic field and orient their flights, and this mechanism involves entangled spin states in cryptochrome molecules in the bird's eyes. The human sense of smell, according to some hypotheses, might involve quantum recognition of molecular vibrational frequencies, not just geometric recognition of molecular shape as classical biochemistry assumed. In each of these cases, biology was not merely tolerating quantum physics, it was actively exploiting it, using tunneling, coherence, and entanglement as functional tools in environments far warmer and noisier than any quantum engineer has managed to replicate artificially. This context transforms the proposal of Hameroff and Penrose from something that seems speculative into something that at least deserves to be taken seriously. If photosynthesis uses quantum coherence to transfer energy with perfect efficiency, why couldn't the brain use quantum coherence to do something classical computation also cannot do with perfect efficiency, which is integrating information in a truly global way, in a manner that produces a unified experience rather than a mosaic of independent perceptions? And here the theory finds its most beautiful intuitive justification. The unity of conscious experience seems to demand exactly the kind of indivisible totality that quantum coherence provides. When you listen to a melody, you do not hear each note separately and then connect them by association. The melody arrives as a gestalt, as a unique temporal shape that exists before any analysis. When you see a scene, you do not first process the edges, then the colors, then the movements, and then combine them into a unified perception, even though your brain does exactly that in the early stages of visual processing. The result that reaches consciousness is already unified, already a coherent and continuous world. This phenomenon, called by philosophers the unity of experience or binding, is one of the most difficult to explain in purely classical terms. If each neuron processes information locally, how does an experience arise that is irreducible to parts? Quantum coherence offers an answer that is not a complete answer, but which is at least an answer that does not ignore the problem. If structures distributed across different regions of the brain enter quantum coherence, they literally form a single physical entity. Binding would not need to be explained as an integration process that occurs after processing. It would be an intrinsic property of coherence. Unity would precede any analysis because it would be a physical unity, not merely a functional one. Now, how can one perceive any of this within one's own experience? It is a question that might seem naive, but which has a surprisingly direct answer. There are moments when consciousness seems especially coherent, and moments when it seems fragmented, when you are completely absorbed in something, when a piece of music or a landscape or an idea captures your attention so completely that you forget yourself for an instant. The experience tends to have a very pronounced quality of unity. There is no separate observer watching the experience, there is only the experience happening. Philosophers and contemplative traditions from vastly different cultures describe this state with distinct vocabularies, but with a surprising consistency in the phenomenological description. In contrast, when the mind is scattered, when several thoughts compete for attention simultaneously, when fatigue fragments perception, the experience has a different quality, less cohesive, more like a mosaic than a painting. This variation in the quality of the unity of experience, which anyone can recognize in themselves, is precisely the kind of phenomenological evidence that theories like Penrose and Hameroff's should be able to explain. And the implicit prediction is that states of higher quantum coherence would correspond to states of greater experiential unity. There are even more subtle manifestations worth contemplating. Think about the nature of insight. That moment when a solution that had been inaccessible suddenly becomes completely clear, not as the result of step-by-step reasoning, but as a sudden emergence that seems to have no duration. Insight does not grow gradually. It appears whole. This is remarkably different from what we would expect from a sequential computational process, but it is exactly what we would expect from a quantum collapse, a process that occurs non-locally and produces defined state from a superposition of possibilities, not as the result of a chain of causes, but as a selection that quantum physics calls non-deterministic in the deepest sense. Think also about what happens during dreams. The dream experience has all the characteristics of genuine conscious experience. It is vivid, it is immersive, it has a quality of presence that seems completely real while it is occurring. But the constraints that organize waking experience, causal logic, spatial continuity, the stable identity of the self, are partially suspended. Neuroscientists know that during REM sleep, when the most elaborate dreams occur, the pattern of brain activity is surprisingly similar to waking in some regions, but drastically different in others, particularly in the frontal regions associated with executive control and metacognition. Could it be that the balance between quantum coherence and decoherence is different during dreaming? That the constraints keeping waking experience anchored in classical physics are partially lifted, allowing a more fluid phenomenology? The system, at this point in the exploration, seems to have found a certain provisional balance. We have large-scale patterns emerging from neural synchronization. We have the possibility of quantum coherence amplifying these patterns in ways classical computation could not replicate. We have the unity of experience as a property potentially derived from this coherence, and we have observable manifestations, sudden insights, variation in the quality of attention, dream phenomenology, that align in suggestive ways with what the theory predicts. It is an elegant structure, almost seductive in its internal coherence. But there is a weight this elegance is carrying in silence, a tension that has not yet fully revealed itself. The balance between coherence and decoherence that makes all this possible is extraordinarily delicate. The same biological mechanisms that could sustain quantum coherence are also the first to become disorganized under certain conditions, certain temperatures, certain substances, certain metabolic states. And if consciousness depends on something as fragile as quantum coherence, maintained at body temperature inside proteins in an aqueous medium, then the boundary between experience and its absence might be much thinner than any purely classical theory would suggest. The fragility mentioned at the end of the previous section is not merely a philosophical concern. It has physical weight, measurable weight that manifests in laboratories and hospital beds and in accounts that defy any simple framing. When the mechanisms sustaining quantum coherence begin to falter, when cellular temperature rises beyond certain limits, when certain foreign molecules cross the blood-brain barrier, when the flow of oxygen to the cortex is interrupted even briefly, something in conscious experience does not merely decrease in intensity, it changes in nature. And this change in nature is where the quantum mystery of consciousness ceases to be a theoretical abstraction and becomes something urgent, something that happens inside real bodies in real moments. Quantum coherence, as established, is not a state of rest. It is a dynamic equilibrium, a constant tension between the natural tendency of quantum systems to interact with the environment and the biological capacity to protect certain structures from this interaction. The microtubules, the membrane proteins, the molecular resonance networks that some theorists associate with the physical basis of subjective experience, all these systems live on the edge of a threshold. On this side of the threshold, coherence is sustained, information integration occurs, subjective experience emerges in its usual form. On the other side, something different begins. This threshold is not a rigid wall. It is more like the surface of a lake on a windy day, where the difference between reflection and turbulence depends on conditions that change continuously. A moderate increase in body temperature, like that accompanying any common fever, already alters the dynamics of proteins associated with microtubules in ways biophysicists can measure. Intracellular hydration rates change. Relationships between tubulin subunits reorganize. Phosphorylation patterns that influence the internal geometry of microtubules shift. Each of these changes, isolated, might seem small, but as in any system operating near a critical point, small accumulated perturbations can produce disproportionately large phase transitions. This is why febrile deliriums have such a characteristic and universal phenomenology. In cultures separated by oceans and millennia of history, accounts of experiences lived during high fever converge with a regularity that would be disconcerting if there were no common physical basis. The sensation that ordinary objects acquire a quality of presence they normally lack, the perception of patterns moving within static surfaces, the difficulty distinguishing between memory, imagination, and current perception, the intensification of certain emotions accompanied by a strange neutrality toward others. These are not simply random hallucinations generated by an overloaded brain. They have structure, they have repeatability, and the quantum theory of consciousness offers a way to understand why perturbations in the physical substrates of coherence would produce exactly this kind of structured alteration in subjective experience. The same principle applies with important variations to the effects of certain psychoactive substances. Research on compounds like psilocybin and dimethyltryptamine, which has experienced a considerable scientific renaissance in recent decades, has revealed patterns of brain activity that classical models of neurophysiology have difficulty fully explaining. The synchronization of electroencephalographic activity between brain regions that normally operate relatively independently increases dramatically. The measure of entropy in neural activity, which functions as an indicator of the complexity and unpredictability of brain states, reaches values exceeding those observed in any other natural state of the human central nervous system, including states of attentive wakefulness, deep sleep, or REM dreaming. Within a purely classical framework, this increase in entropy and synchronization would merely be a set of correlations between measures of electrical activity. But if consciousness has a quantum basis, if what it is relates to patterns of coherence and decoherence in specific molecular substrates, then the question these data raise is different and much more unsettling. Could it be that certain substances do not merely alter neuronal firing patterns, but affect the very quantum dynamics of the protein system sustaining coherence? Could it be that what participants in clinical studies describe as an expansion or dissolution of the boundaries of subjective experience corresponds to a real transition in the quantum regime of their cognitive systems? There is no definitive answer to these questions yet. But there is a fact that deserves careful attention. The phenomenological accounts collected in therapeutically controlled contexts consistently describe a quality of experience that has no parallel in ordinary states. It is not merely about more intense perceptions or freer associations. Participants describe something that seems to be a change in the very way experience is structured, as if the boundary between what is perceived as internal and external, between the observing self and the observed phenomenon, becomes permeable in a way everyday language was not built to capture. This type of account has a name in the phenomenological literature. It is called ego-boundary dissolution, and it also appears in records of deep meditative practices, in certain forms of spontaneous mystical experiences, and, in a less poetic but equally significant way, in documented cases of prolonged sensory deprivation. What all these conditions have in common is that they involve drastic alterations in the flow of information between the organism and the environment, and if consciousness is, in part, a process of quantum information integration, then any condition that radically alters the input or processing of information would be altering not just the content of experience, but its very architecture. Clinical neuroscience finds its most dramatic version of these phenomena in near-death states. For decades, accounts from people resuscitated after cardiac arrest have included descriptions of experiences that defy any simple model of correlation between electrical brain activity and consciousness. The central problem is that the electroencephalogram goes flat, indicating an absence of measurable cortical activity, on average within 20 to 30 seconds after cardiac arrest. Yet detailed accounts, verifiable in some cases through elements the patients could not have known otherwise, describe a continuity of experience that would have occurred precisely during this period of electrical silence. Proponents of the quantum interpretation, notably Roger Penrose and Stuart Hameroff, have suggested that microtubules could, in principle, maintain quantum coherence for a brief period even after the interruption of synaptic electrical activity. If all core processes are, as they propose, fundamental to subjective experience in a way that goes beyond the simple computational function of neurons, then the extinction of conscious experience would not be instantaneous with the extinction of classical electrical activity. There would be a window, possibly on the order of minutes, during which ongoing quantum processes would complete their cycles of objective reduction. This hypothesis is extraordinarily difficult to test. The instruments neuroscientists possess to measure brain activity operate on scales much larger than those where quantum coherence in microtubules would occur. It is like trying to detect individual atomic movements using a seismograph designed for earthquakes. The absence of signal on the electroencephalogram does not prove nothing is happening in the molecular substrates, just as the silence of a radio does not prove there are no electromagnetic waves in the environment. They are instruments measuring different things. What humanity has developed, faced with this instrumental limitation, is an indirect and patient approach. Researchers cannot directly measure quantum coherence in microtubules during altered states or during the final moments of neural activity, but they can build increasingly detailed maps of the correlations between reported subjective states and measurable physical parameters. Each new neuroimaging technique with higher temporal or spatial resolution adds a data point to this map. Each experiment that manages to isolate and preserve nerve cells in vitro under sufficiently controlled conditions to test quantum coherence adds a fragment to the puzzle. Each refinement in computational models attempting to simulate the quantum properties of biological proteins under physiological conditions narrows the range of possibilities. It is a science of asymptotic approximation, where complete certainty may lie beyond what any current methodology can achieve, but where each generation of researchers gets a little closer to formulating the questions with the precision necessary for partial answers to become possible. Humanity is measuring the shadows of a phenomenon it cannot yet illuminate directly. What emerges from this collective and gradual work is a picture of dynamic phenomena that are not discrete states but trajectories. Consciousness in intense mode, whether via fever, substance, deep meditation, sensory deprivation, or critical biological moments, is not simply an increased volume of the same process occurring in the ordinary state. It is a different trajectory in the system's phase space, to use the language of dynamical systems physics. And different trajectories can pass through regions of phase space, where the system's rules of behavior are qualitatively different. In physical systems that scientists understand well, phase transitions are not merely quantitative changes. Water that freezes is not just colder water. It is water in a radically different regime of molecular organization, where properties that did not exist in the liquid phase suddenly emerge. If consciousness can exist in different quantum regimes, separated by phase transitions in its physical substrates, then the dramatic phenomena clinicians and researchers document are not anomalies or system failures. They are coherent expressions of dynamics operating according to different rules. This perspective has a consequence that deserves to be unfolded with care. The structures that emerge during these intense states, the patterns of experience that seem more coherent than ordinary experience and at the same time less anchored to the everyday, the memories of certain altered states that possess a quality of vividness persisting decades later. the reorganization of priorities and values that frequently follows experiences of ego dissolution. All these are not peripheral coincidences. They are indications that the nervous system in intense mode can generate and consolidate structures that persist far beyond the episode that produced them. It is as if the system takes advantage of the temporary opening of a wider quantum channel to record something the ordinary mode could not register with the same depth. An experience of boundary dissolution lasting 40 minutes in a clinical protocol can reorganize a person's architecture of beliefs and emotional responses in ways years of conventional therapies could not. An insight occurring during an intense febrile state can persist with a clarity more ordinary experiences lack. The dream phenomenology of certain nights can leave traces a person carries for decades, unable to explain where they came from. While you rest, somewhere right now, in some intensive care unit or some sleep laboratory, in some sensory deprivation booth or some room where a fever is at its peak, some nervous system is crossing one of these phase transitions. It is passing through the threshold where calm behavior breaks and something more intense begins. And in that nervous system, in the microtubules of its pyramidal cells, in the protein networks biophysics is still learning to describe with sufficient precision, some process occurs that science can measure at its edges but cannot yet illuminate at its center. What makes this even more intriguing is that these intense episodes rarely happen without leaving traces in the world beyond the individual who lived them. They are reported, compared, interpreted, incorporated into traditions and protocols. And in this process of transmission and comparison, something is revealed about the nature of these phenomena that no laboratory instrument could capture in isolation, because the phenomena do not end when the episode ends, and they do not remain contained within the nervous system where they occurred. These traces that intense experience leaves in the world, in the words someone chooses to describe what they lived, in the gestures they change, in the decisions they begin to make differently, are not mere secondary byproducts of the phenomenon. They are a constitutive part of the phenomenon itself. Consciousness, whatever its deepest physical nature, does not operate in isolation. It operates in permanent contact with other systems that also process, also integrate, also respond. And the main of these partner systems, the one with which individual consciousness exchanges energy most constantly and transformatively, is the very network of other consciousnesses surrounding it. This contact between minds does not need to be mystical to be profound. It occurs through language, gesture, imitation, shared emotion, interpreted silence. Every time someone relates an experience to another person, something passes from one nervous system to another, not as a direct transfer of internal states, which would be physically impossible, but as patterns of activation that the receiving brain reconstructs from the signals it receives. What arrives is not the original experience, but a resonance of it, a version the other system assembles with the materials it has available, its memories, its categories, its expectations, its present state. And this reassembled version can generate states that would never exist without the transmission. This means that collective consciousness, if this expression is taken in a rigorous and not metaphorical sense, is a second-order system. It is not the sum of individual consciousnesses, because sums preserve components. It is an emergence arising from the coupling between these individual systems, and it possesses properties none of the components possess alone. An entire culture can sustain beliefs, practices, and forms of attention that none of its individual members would be capable of developing or maintaining in isolation. The monk who meditates for decades in a monastery is not merely cultivating an individual skill. He's participating in a feedback loop spanning generations, refined by hundreds of years of trial, error, transmission, and correction. This feedback loop between individual minds and collective traditions is one of the most biologically relevant phenomena science is still learning to formalize. The data, even approximate, are revealing. Contemplative practices documented for over 2,500 years show remarkable structural convergences with practices arising independently in cultures that never had contact with each other. Groups in the Indian subcontinent, in certain lineages of the Mediterranean basin, in native traditions of the Americas, and in practices developed in isolation in the interior of East Asia arrived, via distinct paths, at sets of techniques presenting significant functional overlaps: breath regulation, deliberate direction of attention, cultivation of specific affective states, alternation between concentrated focus and diffuse openness. This convergence cannot be explained solely by cultural diffusion. Something in the human nervous system responds to certain conditions consistently enough that different civilizations, without communicating, arrived at partially similar maps. What this reveals about the relationship between consciousness and time is particularly fascinating. In the short term, which here means the span of a human life, the individual nervous system is extraordinarily plastic. The changes intensive contemplative practices produce in the brain are measurable on scales of weeks. Cortical thickness in certain regions associated with attention and interoception increases detectably in practitioners with dozens of accumulated hours. Functional connectivity between default mode networks and executive control networks reorganizes in ways persisting far beyond the practice sessions themselves. The system learns, and this learning literally rewrites the architecture of the physical substrate. In the medium term, over decades within a single life, these changes deepen and integrate in ways going beyond simple accumulation. Practitioners with decades of experience do not merely possess more refined skills than beginners, they seem to inhabit qualitatively different basal states. The resting activity of their nervous system already exhibits patterns that in non-practitioners appear only during states of high cognitive demand or during certain types of deep sleep. The system, through gradual accumulation of directed experience, has migrated to a different region of its own state space. And in this new region, the system's behavior, in response to external perturbations, is substantially distinct. The perturbation occurs, but the system returns to its reference state faster, more completely, with less residual distortion. Over centuries, what emerges is something even more interesting. The traditions sustaining these practices function as information storage and transmission systems operating on timescales inaccessible to any individual practitioner. A lineage transmitting meditation techniques for 500 years is not merely preserving instructions, it is preserving accumulated feedback on what works, what does not, which states are productive and which are traps, which mistakes beginners make most often, and how to correct them before they become habits. This feedback traverses generations of practitioners like an externalized collective memory, more durable than any individual nervous system and capable of refinements no isolated individual could achieve. On scales of millions of years, the question changes nature. What is at stake is no longer the refinement of practices within an already formed species, but the very evolutionary trajectory of systems capable of subjective experience. Consciousness, whatever its physical substrate, is a phenomenon with a geological history. The microtubules Penrose and Hameroff identified as possible sites of quantum processing are not arbitrary structures. They are the product of over 500 million years of nervous system evolution, refined by selective pressure in environments rewarding certain forms of information processing and penalizing others. The current human brain is a point on a much longer trajectory, not a destination. This introduces a temporal dimension that completely transforms the question about consciousness. It is no longer just about asking what it is now, but asking what it was, how it came to be what it is, and where this trajectory points. And here the sensitivity to initial conditions reveals itself with all its dizzying consequence. Evolution is a process profoundly sensitive to small differences in origin conditions, The difference between the nervous system of a human and that of a chimpanzee, animals sharing over 98% of their genetic material, is the result of a cascade of amplifications from initially tiny differences. Small variations in regulatory genes controlling the duration of cortical development produced, over a few million years, qualitative differences in cognitive capacity that no superficial genetic analysis would predict. This is the fundamental limit of human prediction when applied to complex systems. It is not just that we lack enough data, although that is also true. It is that the mathematical structure of the problem is such that uncertainty grows faster than any information gathering capacity could compensate. Future states of systems sufficiently sensitive to initial conditions diverge exponentially from any initial description, no matter how detailed. This is not a provisional technological limitation to be overcome when instruments improve. It is a structural property of the possibility space in which these systems exist. And here resides something deserving careful contemplation, because it is simultaneously humbling and liberating. The impossibility of completely predicting the behavior of these systems is not a flaw in human knowledge. It is a reflection of the richness of the possibility space these systems inhabit. A completely predictable system would be a system completely determined by its past, without genuine capacity for novelty. Unpredictability is not absence of order. It is presence of a complexity that simple order cannot exhaust. There is a particular beauty in this condition, consciousness. This phenomenon still defying any complete description, inhabiting the interior of physical systems while seeming to point beyond them, changing when observed and observing its own change, exists exactly at the intersection between the comprehensible and the surprising. It is regular enough to be studied, to exhibit patterns neuroscience can map and physics can attempt to formalize, and it is open enough never to be completely captured by any map, any formalization, any theory starting from fixed premises. The systems sustaining it, the nervous system with its microtubules and its oscillations and its phase transitions, the networks of individual consciousnesses coupling through language and imitation and emotion, the traditions storing and transmitting refinements over centuries, all these systems exhibit this same dual nature. They obey laws, and within those laws they surprise, they have history, and within that history they innovate. They are stable enough to persist and flexible enough to learn. The fact that these properties emerge in physical systems, in atoms, in molecules, in proteins, in cells, in networks of cells, in networks of organisms, without any of these properties needing to be inserted from outside, without any external agent needing to push the system toward complexity, is one of the most quietly extraordinary discoveries of science in the last 100 years. Matter, left to itself under the right conditions, produces systems that experience. This fact, if it is a fact, and the best available evidence suggests it is, redefines what matter is. And it is in this redefinition that something begins to take shape very slowly, like the perception of a form always present in the noise but which the eye took time to recognize. There is, behind all this multiplicity of scales and systems and mechanisms, something that every approach to the problem of consciousness, from completely different angles, seems to touch without being able to name directly. It is not a mechanism. It is not a substance. It is not a law in the conventional sense. It is more like an organizing principle phenomena reveal without exhausting. Something present both in the moment a nervous system crosses a phase transition, and in the moment a tradition of contemplative practices transmits its accumulated refinement from master to apprentice. Something belonging to no specific time scale, and which, therefore, can appear in all of them. This something does not yet have an adequate name in the language of science, but the contours of where it is are beginning, very slowly, to become sharper. This something that lacks a name yet is, curiously, the most familiar thing in existence. It is what makes a system not merely the sum of its parts, but a relationship feeding back upon itself. It is the principle by which a stable configuration does not need an external guardian to maintain itself, because it itself becomes the process of its own maintenance. Consciousness, seen through this lens, is not a final product. It is a cycle sustaining itself while conditions allow, and dissolving when those conditions unravel, just as a flame is neither the wood nor the oxygen, but the dynamic relationship between them while it lasts. Feedback is the central mechanism behind almost everything making consciousness possible. When neurons communicate, they do not merely transmit signals in one direction, like wires in a common electrical grid. They respond to the state of the entire system, and that entire system responds back to each individual neuron. The brain is, overwhelmingly, a system talking to itself. The majority of connections within the cortex are connections returning from higher layers to lower layers, from integration regions to primary processing regions. This means what you perceive is already being continuously interpreted before you even have the sensation of having perceived it. Top-down feedback does not merely comment on the arriving signal, it actively shapes what the signal will be for the levels below it. The brain is constantly predicting the world, comparing that prediction with what arrives through the senses, and adjusting both perception and prediction accordingly. Consciousness, in this architecture, is not an open window to the world. It is a controlled hallucination continuously calibrating itself against the resistance of reality. This cycle of prediction and error does not happen at just one level. It repeats across scales of time and complexity, fitting inside one another like concentric sets. There are predictions happening in fractions of a second, dealing with the position of objects in space. There are predictions happening over seconds, integrating sequences of events into causal narratives. There are predictions developing over hours, days, years, shaping what the system expects the world to be, what it expects of itself, what it expects others to expect of it. Each layer feeds back into adjacent layers. The result is a system not merely processing information, but possessing a model of itself processing information. And it is exactly at this point in this recursivity of models within models that the thing begins to seem like something we could call experience. The molecular dimension of consciousness is where the conversation between quantum physics and neuroscience becomes most concrete and most controversial simultaneously. It has been known for decades that neurons function through electrochemical gradients, that sodium, potassium, calcium, and chloride ions cross membranes with regulated precision, generating the potential differences making electrical firing possible. This process is in itself thermodynamic, probabilistic, sensitive to fluctuations in the medium, body temperature, ionic composition of extracellular fluid, concentration of neurotransmitters in the synaptic cleft. All these factors create an environment where neural computation is always navigating on the edge of a transition zone between order and disorder. It is not a machine operating under ideal laboratory conditions. It is a living system operating at the body's ambient temperature, subject to variations and noise that, in any conventional engineering system, would be considered undesirable. And yet, perhaps it is exactly this noise that matters. There is growing evidence that certain biological processes utilize quantum fluctuation not as a perturbation to be eliminated, but as a resource. Photosynthesis, as studied in detail in recent decades, seems to transport energy in ways exhibiting quantum coherence, at least on very brief timescales. The proteins involved in these processes have structures seeming to have been evolutionarily selected, not just for stability, but for the capacity to sustain these coherences long enough for them to do useful work. If this happens in photosynthesis, the question of whether it also happens in some part of the neural machinery becomes legitimate, even if still unanswered. The microtubules of the cytoskeleton, the integral membrane proteins, the enzymes regulating neurotransmitter release, All these structures have dimensions and dynamics, placing them in the frontier zone, where quantum behavior begins to be relevant. The problem is that the cellular environment is too warm, wet, and noisy for delicate quantum coherences to survive long enough to influence processes on the scale of neuronal firing. This argument is powerful, and most physicists working with open quantum systems consider it decisive. But the response from those defending quantum relevance is not to ignore this argument. It is to ask whether evolution could have developed protection mechanisms against decoherence, analogous to those engineers try to build artificially in quantum computers. There is no proof of this, but the question remains open, and it remains open precisely because the deeper question, the one concerning subjective experience, still lacks a satisfactory mechanistic explanation at any level. The integrated system consciousness appears to cannot be reduced to any of its layers without something essential being lost. Not because the laws of physics cease to apply at some point, but because physics, as practiced to date, specializes in describing structures and processes, and what needs explaining in consciousness is not merely a structure or a process. It is the fact that there is something it is like to be that process. The distinction seems subtle, but it is the distinction separating a camera from an observer, a thermometer from a creature feeling cold. The camera records, the thermometer measures, but neither has the experience of seeing or feeling. The question about consciousness is the question about what makes a physical system do more than record and measure. What makes an internal perspective exist, a quality of what happens, or what it is like. When looking at the field as a whole, at the contributions of non-equilibrium systems thermodynamics, integrated information theory, mean field approaches in neuroscience, contemplative traditions mapping internal states with a systematicity it would be disrespectful to ignore, what emerges is not a clear answer. What emerges is something more like a convergence of contours, different methods, different vocabularies, different intellectual histories, all arriving at the same region without being able to enter it completely, as if the object they approach had the property of receding slightly every time a more precise description is attempted, not because it is illusory, but because it has the nature of being that which describes, and not merely that which is described. Emergence is the name science has given to this capacity. Systems have to produce properties not present in any of the components taken in isolation. The liquidity of water is not in any water molecule. The capacity of a beehive to regulate its temperature is not in any individual bee. The capacity of a market to set prices is not in any buyer or any seller. Emergence is not magic. It has mechanisms which can in principle be described. But describing the mechanisms does not eliminate the fact that the emergent property is real and behaves according to its own laws, laws not appearing in any description of the components. Consciousness, if it is an emergent property, is the most radical emergent property known, because it is emergence producing the very perspective from which all other emergences are observed. Ultimately, consciousness is simply the way the universe observes itself. This synthesis might seem too poetic to be scientific, but it is actually the logical consequence of taking seriously each of the approaches the previous parts of this exploration traversed. If information is the fundamental substrate, then a system integrating information complexly enough not only processes data from the universe, it is the universe processing data about itself. If quantum theory describes the most fundamental level of reality, and if observation has a genuine role in collapsing possibilities into events, then a conscious system is not an external observer of the universe. It is the universe exercising its capacity to make real what was previously merely possible. If contemplative traditions arrived via radically different routes, at the conclusion that observer and observed are at some deeper level the same thing, then they were articulating the same intuition, contemporary physics begins with much more hesitation to circle. Every element we have traversed returns to this point. The phase transition in the nervous system, which showed how qualitatively different states can emerge from continuous quantitative changes, is the universe reorganizing its own self-observation, information integration, seeking to mathematically measure how much a system is more than the sum of its parts, is an attempt to quantify the degree to which the universe folds back upon itself at a particular point in space and time. Contemplative practices, with their careful cultivation of mindfulness and presence, a consciousness refining the instruments through which the universe sees itself. Quantum decoherence, which seems to separate the classical world from the quantum world, might be the process by which the universe establishes the distinction between observed and observer, a distinction that is real and useful but which is not, perhaps, the ultimate distinction. All of this does not solve the hard problem of consciousness, but it begins to seem less like a problem and more like a feature, less like something physics would one day need to eliminate from the description of the world, and more like something every description of the world must eventually encounter as its internal limit, the point where third-person language meets the irreducible reality of the first person, the point where the map touches the territory in a way unlike any other. And now, in this moment, thought can begin to gently pull away from these depths. Consciousness continues its work while you rest. Neurons still communicate in smooth, slow patterns, the architecture of sleep taking over, reorganizing what was lived. Cells continue their molecular dance, gradients balancing, membranes doing what they have always done, with the silent fidelity of processes that never needed your attention to happen. You are safe. The universe takes care of you. Everything is exactly as it should be. As you rest, consciousness continues being what it always was, this mysterious way the cosmos turns toward itself in a point of light and warmth called life. You do not need to understand this now. You do not need to hold on to it. You can let go. You are part of this. You always have been. The mystery is not outside you waiting to be solved. It is you, breathing, existing, being. Every exhalation takes you a little deeper. Every passing thought is like a cloud crossing a sky that does not move. You are safe. The universe takes care of you. Everything is exactly as it should be. Let the weight of the day dissolve. Let the questions rest. Let the mind quiet like the surface of a lake after the wind passes. The consciousness that you are remains present, but softer now, quieter, touching the shores of sleep like a wave losing its shape upon meeting the beach. You are safe. Everything is exactly as it should be. The universe takes care of you. Good night. The cosmos continues its silent dance, and we rest within its embrace. Thank you for walking alongside me tonight. Sleep well.